So today I'm playing music again, like it happened last year. But today we develop our application much better, and probably outside it doesn't look very different, but inside it's really different. So I'm going to explain how it's done briefly, and actually it's running on this hardware. So this is a three boards, and the USB board basically using as the power supply. And of course, at the very last step of my presentation, I'm gonna load some program from the PC, and in that case, USB is used as the interface to load the program. But right now, I'm gonna use it as a power supply. So basically, only two boards are working: the main board with the SPI flash and C-Force chip on it, and the MIDI board with the MIDI connector and audio connector. So all the calculation, all the bit conversion like RS-232 driver and MIDI parser are done on the C-Force. So a few words about the keyboard. This keyboard is just like a computer keyboard. Just generate play this note, this loud, this long. That's it. Or stop playing. So it doesn't generate any sounds. All the sounds are generated on C-Force. And the way it is generating the sounds, it synthesizes the sounds, is, this way. So basically we have a one node connected to the SPI flash, and SPI flash can keep up to 32 presets or instruments or applications. And basically every preset or instrument is a stand-alone application. You can, in this particular case, this is the music instruments, but it could be a DVD player or some digital voltmeter. Jeb just explained us. So it doesn't matter, because every sometimes we call this overlays or application applets. So this is the structure which will be sent to this port, and from this port it will be distributed across the chip according to the information about the positions and the connections included into this format. So this is the SPI flash with 7 instruments in it, and we have space for 32 instruments. And this is a relatively small SPI flash. It's only 256 kilobytes device. So if you use the bigger one, then you could fit more instruments into the bigger one. And this is the MIDI keyboard, which is connected to the Note 33. So basically Note 33 run the RS-232 decoder. We're just waiting for the start beat and then start counting and decode the serial bits into the words. And then it is connected to the controller and the voice scheduler and the note tables. So after all, this block of blue cores form command to the voice. Which note, which voice, which note, and with which loudness should play. And you can see that the topology of this application is kind of the chain, and sometimes we call it command chain. So this chain starts in here, goes here, this way, and then it goes to the buffer, and finally it goes to the digital analog converter. And we're using the hybrid scheme of digital analog conversion, and it provides us with 18 bits accuracy, virtually 18-bit accuracy at about more than 200 kilohertz. So this is better than CD quality, because we use the pulse width modulation combined with the amplitude modulation. And basically each voice is a pair of cores, and of course for every algorithm, for every other kind of voice, we run different codes inside the voices, but we find out that normally it's just supposed to be 2 cores. Sometimes one core is just a memory server. For example, with the guitar, one of the core, the dark purple cores are just the delay. So and delay basically memory or the cyclic buffer. For the different voices, we keep envelopes, information about how loud we should play the sound during the sounding, I mean, of one single note. But the structure, the topology of every instrument they are very similar to each other. So I will not explain the topology for every instrument, for every preset, and this is basically how it's built and how designed. By now we have 7 different instruments, and we have another instrument which wasn't integrated into the thing, and I believe we will have all 32 of them, but it's not important, because since we know how to do it, we can make the progress really quickly. So I'm going to play the very first preset, which we call bell. So this is the explanation of this voice. So basically it implements the well-known for musicians or people who is doing the music synthesis algorithm called Claude Risset's algorithm. And this is the bell model, and it's using one of the popular method of music synthesis, additive synthesis, where you basically have a lot of sine generators or oscillators with the separate envelopes, and you just add them together to synthesize the particular sound. And it provides us, the 40 cores minus the digital analog converter, and the MIDI controller provide us with the space for 15 voices. And for every voice we have it's not analog, it's just what it sounds like, and it's not wannabe. it just sounds like it's not worse than the Kawai K5. So if you compare them side by side, then our sounds is very competitive. So I'm going to switch to the different application, and it will take just milliseconds to reboot all the cores with the new instrument. So I just switch and get new sound. And we got a pitch bend wheel, so it's working too. So this is very futuristic, modern sound. Well, actually not that modern. I believe the sound came from 70s. Well, it still sounds modern. So this is a Foreman suite-like effect. So something like the old Moogs were playing, and the synthesis it's not a pure kind of synthesis. In this particular sound, we combine different kind of synthesis into the single voice. So this is a combination on virtual analog and wave shaping, and it's the polyphony of this sound is 15 voices, and it's similar to the sounds generated by Clavia Nord modular. And I'm gonna play some other note. You know what? I believe I just switched to the organ, but I'll play on guitar, And this is the this is the model of not church but transistor organ. So, these days the professional musicians, they are looking for some old instrument, they are looking for some vintage sounds, and we can do it very well. Because the biggest difference of this synthesizer and the one you can buy in Fry's or Costco for $100, like Casio and Yamaha, this one does real music synthesis. It generates every sample. And those models, they have a pretty huge library of the samples, pre-recorded sounds, probably from the physical, I mean, the real instrument, and then they just scale them down and scale the amplitude and the tone to generate different notes. And you know, sometimes it's okay, and you know, for the beginners, it's perfect because you know, it's just playing like a Steinway grand piano. But the thing is, if you buy, you know, 3 of them, every of them would play exactly the same Steinway. So you use the same velocity when you press the key, it will generate the same sound. So it's not unique. It's just, you know, the clone Steinway. It's kind of synthetic. And this one, well, since we have no Steinway sound yet, but when we implement it, it's going to be unique because it's real synthesis, and we're using inside the algorithm we got a random number generator, so it generates pretty individual sounds, and it's much closer to the real instruments than the sampled music synthesis. Okay, I'm gonna switch into the, and this is strings. This is what you just heard. This is pulse width modulation combined with a low pass filter, and the synthesis is virtual analog. And 2 words about what's virtual analog is. So virtual analog is how the Moogs synthesizer were done. So you've got 3 kinds of oscillators: triangle wave, you've got rectangular waves, you got the sine, and then you combine them together to generate different sounds. So this is how we synthesize the sounds in our model. And because some of the restrictions of our previous run bias, the polyphony of this voice, of this synthesis instrument is restricted to 14 notes. I believe, yes? How many notes together you can play? And the next sound is electric piano. So this is very Yamaha-like sound. Okay, yes, right, sorry. I think it was beautiful. So it's using frequency modulation, and it's using 4 operators. So basically we have 4 sine generators connected to each other, and each of them control the frequency of the second in the stack. So with the 4 operators you can generate pretty sophisticated sounds, and right now we just generated or synthesized the electric piano sound. This is a pretty vintage sound. The next one is the Oberheim brass-like sound, and it's using the frequency modulation too, 4 operators. But because we have different parameters, we connected in a different way, it will generate absolutely different sound. What else? Okay, let's return to the... And this is guitar. And this is based on physical modeling, and we're using Karplus-Strong algorithm. And, well, I believe you heard it before, but this is still my favorite sound because it sounds just like a real guitar. You cannot distinguish it from the real guitar. And it's absolutely better than everything any classical guitar synthesis I've heard ever. Okay, so yeah, I understand that today there was too much music, so I'd like to switch into some a little bit more technical slide. And this is the list of the functions we have in our room bias right now. And we could fit so many functionality into our applications because we are using this library. So basically we have the helper to calculate the polynomial, and it's very important if you do some mathematical calculation, because a lot of things could be, this functions have a story, because I remember one day Chuck said that it would be good if we could implement the hard computer approximation book as a library, and well, this basically is a hard book. Well, yeah, of course, for every function you're supposed to call this polynomial with the different coefficients, but that's it. So it's done. And the next one is and we have three different kind of yes, it's enough. Three different kind of multiplication. We have a 35 bits integer multiplication. We have two kind of fixed point multiplication, and of course it could be achieved because we use very powerful technique in our coding. We use multiple entry points. And unfortunately, you cannot use multiple entry points in a standard forth, but we use it, and that's why you can fit all of this into just 64 words of memory. And although we got the one function called taps, which is a very powerful helper to build the filters. And we've got the division modular, which is working with the double length numerator. We have a table linear interpolator, and so basically you can dedicate the whole memory of the core for the interpolation table, and then you call this function from the ROM bias, and it will provide you with the data. So I believe if Jeff used this function in his application, he could fit it probably in one less core. That's right now. Well, and this is the triangle. Actually, this came from the Novix library, and we use it as the trigonometry helper to build the sine and cosine function. And we have a relay, and relay is the brick we built our. I explained to you how the control chain is working. So this control chain is built on top of this relay function. So basically, every node is sleeping on the port, and it can execute the command and generate the next add-on to the next generated samples, or it can work as the transport agent. It can bypass some message or program to execute to its neighbor. And we find out this very helpful function, and that's why we built it into the ROM bias. And obviously we have the driver for digital analog, for the digital analog nodes, and we have inside the ROM bias we have drivers for the all booting nodes. So every node you can use as the bootstrap node has its own driver. So you can boot from RS-232, from synchronous serial, and from SPI flash. And now I'm going to run some small demo, and I think not very few people from IntelliSys saw this demo, so it's kind of surprise. So what I'm going to do right now, I'm going to tell to the board to not boot from SPI flash because I'm going to boot it from the PC. So I'm going to disconnect it first. I put a jumper which say don't boot from SPI flash. I connect it to my Linux machine. Okay, let's try now. So this is not speech synthesis. This is singing synthesis. And let me explain what you just heard. Okay, yeah. So this is FOF synthesis. And right now, it was trying to sing for you the word C4. So it's kind of hello world, but you know, we saw hello world right now, and you know, I'm just trying to be original. So instead of hello world, which is a little bit more difficult to say than C4 because there are too many consonants. And by the way, well, this is C4, so the thing is introducing itself, so it's pretty logical. So FOF is a kind of synthesis used to synthesize the singing. And it's very good to synthesize the vowels. Because singing is about the vowels, it's not about consonants. You know, when you in the opera, it doesn't matter, you know, if they're singing in Italian or Russian and English, because you know what this story about. So you just, you know, came to listen to the music. And this is very natural, because in a bel canto technique, the consonants, you're not supposed to pronounce them at all. The vowels is important. So this is the kind of synthesis is very good to produce the vowels. But we wanted it to say C4, so we added the consonant synthesis on top of the vowels, and that's what we got. And eventually, this algorithm will make into the presets, and we're gonna have an instrument. I don't know how we should call it. You know, horse or human. But I think I thought it would be, you know, very nice to have this kind of demo. So this is the version of our Hello World, and it's using 24 cores right now. Questions? Yes?
When are you going to sell it? It's to the public.
Well, actually, it's not my question. Yeah, I think we will.
You're intending to make a product.
Probably. Well, at least, you know, I think that right now the quality of the product is very high, so it's very reliable, and basically everything is done on 2 chips, SPI flash and C4, digital analog conversion, the MIDI interface. So it's supposed to be, you know, much cheaper than the existing products, and the quality is awesome. Okay, thank you.